taking charge, we're taking out the company.
Alright, okay, so probability. So we're going to fly through this as quickly as possible. As I say, you don't really have to write much on here. Pretty much the things that you need are already complete. But you may want to add stuff, so let's take it. So sample space, it's a list of all possible outcomes. Generally given U. So you may have been used to in GCSE with the fancy E. Do you remember that fairly E thing? They now have a U, which is also a bit confusing because it looks very much like a union when it comes to set notation.
That's right.
Okay. So in the exam it was union, but so just be careful. It should be obvious. They don't often, to be honest, they don't often write it, but they change an ID to go back to you. If we talk about an event, we don't talk about past, we're going to, it's the thing that we're interested in. So for example, if we want to roll a 4, the event is rolling a 4. Okay, so that's what we're looking at. So in general, the probability of any event, so it would be written with a big P to show probability. You'd often assign a letter to it, so you would say that rolling a 4 is event A. So the probability of A happening is the number of times that A is possible over the total number of possible outcomes. Okay, so in other words, how many ways can set A happen over the number of things in the sample space, or how many possible outcomes are there? Yeah, so within probability though, we've got experimental probability and we've got theoretical probability. So experimental probability would be for a particular dice. So that particular dice, we do an experiment about it, we then predict what's going to happen with that dice. If we are talking about theoretical probability, we just say, well, there's 6 sides, there's only one of them that's 4, so the probability will be 1 out of 6. Okay? So it does depend. The majority of the time you will be looking at the theoretical probability. Well, I say that. Then you shut up. But that's why things sometimes differ, because it's either an experiment happening or it's theoretical, just this is the number of options, this is how many are possible that we're interested in. Maybe I should stop drinking at lunchtime. I drank it at lunchtime. FYI.
You can Sue with Paris and now.
Sue? What are you doing?
Oh, I'm not getting my money for this
advice. You're just calculating. Maybe I need to take our sources that you already borrowed another one. Right, okay, so when it comes to, do you remember this dash? Not. Yes, excellent. So the probability of A happening plus the probability of A not happening will always equal 1. Okay, so be careful though in that, remember, if you have situations like sports games, you can win, you can not win, okay, so those probabilities will always add up to 1. But you can't say win is something and therefore lose is something else, because you've got that third option. Okay, so the not literally just means not this. Does that make sense? Mm-hmm. Sometimes people look at me and I'm not sure if you're looking going, huh? Or I'm just rambling. Right, this intersection sign. Okay, this means that A and B both happen at the same time. Okay, so it's a combined event, so that means they're both happening at the same time. So the probability, so who does chemistry? Okay, so I would say the probability of people being in Miss Harrison's maths class and the probability of doing chemistry, they're my 2 situations. Then you 3 would be in that intersection because you do both. Yes? If we were talking about Venn diagram. So that's why we put one here. To show that we're talking about the intersection. So these guys do both. A union B means that we're talking about everyone. So we would include everybody that does chemistry, so everybody, all of your classmates, and all of you guys. Yes? All clear with that? Obviously, if we were just counting those people, we can't say the probability of chemistry and then the probability of Miss Harrison's math card, because these three are in both of them. Right? That's where it comes down to now here, in that if we're talking about the union of something, it would be the probability of one event happening plus the probability of another event happening, but we must take away the probability of the intersection, because otherwise we've counted those twice. That makes sense? Mm-hmm. So Jen, if I say the probability that people take chemistry, so if I cancel the people that take chemistry, there's 10. And then I say the probability of Miss Harrison maths class, 8. I wouldn't therefore say there's 18 people that do chemistry and or Miss Harrison's maths class, because 3 people do both. Does that make sense now? So that's why we've got to take away this intersection.
So it'll be like 10 minus 8.
No, 10
No, we
minus
might
8
10
minus
10
8.
minus 10 plus 8 minus
3.
minus 3. Yeah. I mean, obviously we're talking about these random numbers.
Yeah.
But we can also see from the diagram, because A would be this whole circle, B would be this whole circle, and we can cancel that little bit twice. Okay, so that's the important thing here. Now, you do get given this formula. Okay, so that is in the formula booklet. Right, let's have a look at this example I've got here. So a card is selected at random from a pack of cards. So you don't generally talk about cards in IB at IB level, but you're all aware of packs of cards and what how they're made up. Does anyone sit there?
How many cards is 30 to 50? There's 52.
30?
52. I think 30.
Unfortunately, it was recorded,
You mean all of those gasoline added for those tiny packs are cards? So if you ever want to win some money, place your bet. Do not place your bet on Olivia. You will win. That's what
chill out. Right, so there's ace through to king on both in all 4 suits. Yes, half the red, half the black. Lovely job. Okay, they don't often do it, but just in case. So, if we're talking about probability that we've got a king, alright, there are 4 kings in a pack of cards out of a possible 52. Probability is the one time you do not have to reduce your fractions. Okay, so you don't have to simplify, you can leave it as 4 over 52. You will often find that a lot of the questions are also decimals rather than fractions, but the rules still apply. Okay? Oh, which I should backtrack a little bit. Where we've got here that the probability of an event plus the probability of not an event is 1, means that your answers can never be more than 1. If someone says what's the probability, it has to be less than 1. It's also not going to be negative. Okay? So be conscious about what you're writing when you're writing your answers. Make sure your answer is not more than 1, and make sure it's not any negative value.
So the question's giving you like in fractions, so like you might answer in fractions or vice versa?
Probably, yeah. It's probably going to be easier in that format. No, it would be all equivalent. It totally would be all equivalent. And it would also normally accept a percentage as well. So if you change it to a percentage. Some people, for some reason, you hear the word probability, it has to be read as a percentage. So it's fraction, decimal, or percentage. Now, when I'm saying your answer can never be more than 1, that doesn't include something like the probability of getting something is so-and-so, we toss a coin 600 times, how many times would you expect to land on so-and-so? That answer is going to be more than 1. Okay, so when I say probability, your answers cannot be more than 1, it's only if they're asking for the probability of an event. Okay, right. Okay, so there were 4 kings, 52 out, and then reduces to 113 if you wish. Next one is a heart. You've got a couple of choices here. You can say, right, well, there are 13 cards all with a heart on them out of a possible 52. You could have gone straight to the simplified version because you know there are 4 suits, and only one of those suits is a heart. So you could have gone straight to the 1 over 4. Okay. A king of hearts in a pack of cards. How many kings of hearts do you have? Should you have? What? Unless it's a dodgy pack, in which case you need to return it. So you've got one of those out of a possible 52. So 1 out of 52. And either a king or a heart. Okay, so we've got a king or a heart. So here we'd start to think about, well, a king or a heart means that we're talking about a union. Are you all happy that or would indicate that we're talking about the union of them? So the probability of the king we worked out, the probability of the heart we worked out, but we have to subtract the probability of it being the king of hearts. So that would be the intersection. And so that's where we would use that formula. So we'd have 4 over 52 plus 13 over 52 minus 1 over 52. In these questions, the fact that we haven't reduced them is actually making our life a lot easier because they're fractions, because we know that when we're adding and subtracting, we need to have the same denominator anyway. So just be aware, don't always rush to reduce them if you're working with fractions. And we get 16 over 52 or 4 over 52. Okay, anything else? Mutually exclusive. If two events are said to be mutually exclusive, it means they've got no outcome in common. So in other words, there's nothing in the intersection. Okay? So if we were drawing as a Venn diagram, then we would probably draw the two circles separate. Okay? So if there was nothing in the intersection, they would be drawn separately. And in this situation, then the union would simply be the probability of A plus the probability of B, because we don't have to worry about subtracting anything because there was nothing in that intersection. Yeah? This fact is sometimes used to say, show that something is mutually exclusive. So they'll say, they'll give you some information and you have to manipulate that and show that the union is equal to just A plus B. Exhaustive events just means that there's nothing outside, essentially. And so the union would equal 1. So when we were talking about Venn diagrams, remember sometimes in the past we had things outside here. If it was exhaustive, it's all in here. There's nothing on the outside. Because remember the probabilities of events happening always add up to 1. Yeah, so the union would have to equal 1 if it's nothing on the outside. Yeah.
Back up with mutually exclusive events. It says there's nothing for the intersection, so how come there's the union? Or that was just separate?
Because remember up above we had the union was probability of A plus probability of B plus B minus the probability of A intersects B.
Yeah.
Well, because there is nothing in that, it means that this is 0.
Oh, okay.
Yes, so you wouldn't have to worry about it. Sorry, really itching my nose. Right, here's some information. So we've been told that the probability of X happening is 4/5, the probability of Y is 1/2, the probability of intersection is 2/10. Show that the events X and Y are exhaustive. Alright, so we get given this formula. I've just changed the letters for you so you're comfortable. And so we've gone from A and B to X and Y. We know that X is this, Y is this, they've told us this, jubbly. So we've added up these bad boys and we've got it equal to 1. So because the union is equal to 1, then they are X.
If they give it to you and they're not the same denominator, can you change the denominator?
Yes, so that's how you would change it. So if it was on paper 1, you need to remember how to add and subtract fractions. Which I know because some people always like. If that's an issue then. But as I say, to be honest, more they do decimals. So hopefully it will be easier.
So you won't get it on the non-caption?
If they do, it might be decimals, but
Really? How are you supposed to do that on a normal calculator? Are you supposed to like add and subtract that? Without a calculator? Oh, like simple.
It's gonna be less. It's gonna be different.
Okay. I'm thinking of
so
like
less,
super.
it's going to be less than 1.
No, I was thinking, yeah, like I was thinking.
Yeah.
Oh, like her curtains.
yeah.
Right, conditional probabilities where it starts to get a little bit more complicated because we're limiting our population, if you like. We're limiting our sample space. Okay? So this kind of situation is that you're given this, Okay, so what we're saying here is the probability of A happening given that B has happened. Okay, so this is the kind of situation where I'm saying, I could say, right, given that you're in Miss Harrison's maths class, what's the probability you do chemistry? So the fact that you're in Miss Harrison's maths class means that we're reducing our sample space to just 8. So our denominator would now be the probability that you're in my class. Okay? Or in other words, there's 8 people, so our denominator would be 8. Whereas before, if we were just saying what's the probability of things happening, we're talking about the whole of IB2. I didn't say that, but that's what we were saying. Yes. But now we're saying, right, I don't care about the other people who do chemistry. I'm only interested in the people who do chemistry who are in my class. So it's a probability you do chemistry, given that you're in my class. So we've reduced this number now to just 8. And this means the probability you do chemistry and also in my class. And that's where we get those 3 people from. Does that make sense? How do we not really? Okay, so this, given that, is, so it's A, given that B has already happened. Okay, so you're cutting down the options. Right, 2-paired die thrown, the probability is 1 dice shows a 4, F, given that the total of the 2 dice is 10. Alright, so sometimes, okay, you're just given these words and it says, right, go off, do it. So you actually have to think about the probability of this event happening. In order to do that, it's often a good idea to jot down or sketch the sample space that you're interested in. So for this, I've got, essentially I'm saying that I've got dice 1, 2, 3, 4, 5, and 6, dice 1, 2, 3, 4, 5, and 6. So when I join them together, I've got a 1, 1, a 1, 2. These are all my different possibilities. Okay, do you want to do that? Yeah. Sometimes people are rubbish at doing this. If their head's going all over the shop, they're in a test anyway, it's all going a bit pear-shaped. So you need to try and find the most logical way in which you can make sure you're including everything. Okay? Hopefully this looks logical to you. So I started with 1, that's 1, 2, and then it started with 2. So they are my different options. So I can see that I've got 36 possible outcomes. So my denominator for these events is going to be 36. I then have to have a look to see what they're asking us. So the probability it shows, or actually what am I doing? So F intersect T. Okay, that means that we've got a 4 and our total is 10. Okay, because F meant that we were thrown 4, and the T meant that the total of our dice is 10. Now looking at these options here, these 36 options here, it's only these 2 that satisfy both of those conditions. Yeah? The probability that it's a 10, the probability that it adds up to 10 is only these 3 situations. Okay? So that means that the probability of the intersection is 2 over 36. The probability of the T is 3 over 36. So if we're now following this formula, sorry, actually, find the probability that one of the dice shows a 4, given that the total of the 2 dice is 10. So, 4 comes first, this is the F, and then given that 10 is our total. So, comparing our letters, and whilst you may look at that and go, really? The way they write it can sometimes be confusing, so you do need to make sure that you've got the correct thing on the right hand side. Yes? So remember how I was just saying about how before we were looking at the whole of IB2, and then I said I'm only interested in the people that are in my class that do chemistry. So that's what they're saying. They don't care that there's 36 different options. Okay? They're only interested in how many of these have a total of 10? And of those, how many of them have 4 of them? Yeah? So we've got 2 over 36 over 3 over 36. We divide fractions. How do we divide fractions? What's the rule?
Reciprocal of the 36, so 2 times 36 over 3.
So it becomes 2 over 36 multiplied by 36 over 3, yes? And then they cancel because you've got one on the top and bottom. So it's just 2 there. Okay, so that's how you would divide fractions if you can. Make sense?
There was 6 over 36 minutes over 5.
No, it was never 6 over 36 because I had 2 options here. So the intersection was 2 out of 36.
Yeah, I need multiplication. Was it 2 times 3 over 36? Like, after you cancel the 36 and 36 out, was it 2 times 3?
Oh, there's a 1 there now because I've divided top and bottom.
Oh, okay. I got you.
Is that what you meant?
Yeah.
Yeah. So once they've gone, it becomes 1. Okay, here's another example. So they've told you probability of A. They've told you the conditional probability of A given that B happens. And they've told you the union. Okay? Find PB. Right, so A given that B happens. Okay, so we know that's what I've done to replace my 1/4. Okay, so that's from B. A intersect B. Well, have I given that information?
No.
Not yet, no. Okay, so let's deal with that in a second. Probability of B, you want to know that? No. Okay, so far we're looking like we're in doo-doo. Okay? We're not. They're not. I can rearrange this though. Yes? So I can say that the intersection is equal to 1/4 multiplied by the probability of B. You're happy with that? So essentially I've just multiplied by PB, both sides. So I've got that as a statement. You will work with me just for now. Okay? Because the reason I did that is because if you recall, you get given this formula, but you get given another formula as well that does have some of the other information in here. So the other formula you get given is this one. Yeah? So that means that the union, which we know to be 2/3, is equal to the probability of A, which we know to be 1/2, plus the probability of B, subtract the probability of the intersection. Now we just said here that this intersection is 1/4 of PB. I mean, if you would prefer, we can call this a letter if you want. I don't know, would you rather? Let's keep it like this. So, subtract 1/2 from both sides. Okay, so I've now got 2/3 subtract 1/2. And then I've got 1 whole PB, subtract 1/4 PB, gives me 3/4 PB. Yeah? Maybe I need to do this bit to the side. How do we subtract fractions? Well, we need to have the same denominator for both of them. So I want to have a 6 on both sides. Are you okay?
I'm confused about 3/4.
Because this is 1 PB, subtract 1/4 PB. So 1 whole 1, subtract 1/4 will be 3/4. Okay? Because 1 whole 1 needs to be 4 fourths. 4 fourths. Quite hard to say, 4 fourths. Okay, so going back to this, we need a denominator of 6. So that means we have to multiply top and bottom by 2 on this side. And this we have to multiply top and bottom by 3. So that's 4, 6, subtract 3, 6. Gives us 1/6. So I did it for you, but just in case it's on paper 1, and you don't have your calculators there to chuck in, you may need to do stuff like that. Okay? So then if I know that 1/6 is equal to 3/4 of PD, and they've asked us to find the probability of B, that means that I can then rearrange this however you would want to do it. What would your, like, what's that? No? Yes? Perfect. So then we've got 1 multiplied by 4 over 6 multiplied by 3, which gives us the 4 over 18, which reduces down to 2/9. Alright? So it's not always super cut and dried, and sometimes you need to look at, say, okay, well, what information have I got? What other formula can I use to help me? And can I combine all that information together to find the answer? You all got that down? Yeah. Independent events, so they're said to be independent if you're saying that the probability of A happening given that B happening is exactly the same as the probability of A, then it means that B has no effect on it. Does that make sense? Mm-hmm. So if you're saying the probability of A given that B has happened is equal to that, it means they're independent. So the situation could well be that they'll say show that these events are independent. So you're going to find a value for the conditional probability and hopefully find that it's the same as the probability of A. The formula for the conditional probability is this, left-hand side. Yes. If we're saying that's equal to PA, then we can rearrange this to say that the intersection would be these two probabilities multiplied together. Card is picked at random from pack of cards, and a fair die is struck. Find the probability of the card is ace of spades, so we call that AS. And the die shows a 3. Okay, so there's the two situations. Firstly, we need to identify these events as dependent to enable to use the above formula. So, hopefully you all appreciate that roll a die, pick out a card, the two are not going to affect each other. So the intersection would be 1 over 22 multiplied by 1 over 6. Yes, remember that? Top times top, bottom times bottom. 1 over 3, 1, 2. Done. Okay, pretty easy. Last bit's tree diagrams. Do you remember these? Okay, if you have an equal sign in between, that's when you would cross multiply. So if you're just multiplying, it's top, top, bottom. Alright, okay, we're at 28 minutes ready. So tree diagrams. I have another bit of a tree diagram.
I love tree diagrams.
So, here's just a big one here. So remember, with tree diagrams, you're looking at, so this is one thing happening, and then this would be the second one happening, and then that would be the third time it happens, okay? So when you're talking about that, you're saying, right, which are my options? So here what we're doing? I shouldn't know. Skip that. So we've got bags and we've got discs in the bag, we're taking stuff out, okay? We haven't replaced them, so I've gone straight for a non-replacement one. So remember that for each branch, if you like, so for each portion, these probabilities, I've just totally lost these probabilities have to total 1, okay? So for this branch here, these probabilities equal 1, add to 1. For this branch, they add to 1. For this branch, they add to 1. Okay, so for each of your options, now if you have 3 options, obviously those 3 probabilities have to add together to give 1. Here I haven't replaced it. So if I took a red disc out, initially I had 9. I've now reduced it to 8 for my second set. I always think it's easier to fill in your numerators as you go. So your red numerator would have reduced by 1, but your blue wouldn't have done in this instance if we followed here. And we know that 3 plus 5 gives us 8. That has to 21. If we'd followed the blue here, our blue would have reduced to 4, and the 4 is still on the red. Similarly with blues, with blue, so it's now gone down to 7s. If we want the probability of a red and a red and a red, then we would multiply those two probabilities together, and that would give us 24 over 504. And note, they do simplify, but I've kept them as their big numbers because we may need to add and subtract stuff. And if you want more than one situation, remember that once you've done these probabilities, you would then add any situation you're interested in. So if you want to know the probability of getting 2 reds, we'd be looking at that one, and that one, and that one. So we would add these probabilities together, for example. I don't know, what example do you write that? So what's the probability of 2 reds and 1 blue? Check to see which one's got 2 reds and 1 blue. Oh, that's really weird. That is what I just said about 2 reds. Huh? I know.
And you're wearing
You can't appreciate that. So we would add these together, and so we've got 180 over 504, and this is step. So you can leave it like that, or it reduces down to 5 over 14. Okay? So that's probability in a nutshell. The joyful